But let's start with the problem. So two students are trying to figure out the following antiderivative. And we could read it as finding the antiderivative or the integral of 2 times x plus 1 over 1 minus x cubed. And the first student, Jesse, works on it and gets an answer. 1 plus x squared divided by 1 minus x quantity squared. And of course, because Jesse wants full credit, plus c. Good job, Jesse. Now Tracy, on the other hand, comes up with an answer of 2x divided by 1 minus x squared plus c. Now the question is, who is right? Now, when you're working on things, it's not unusual for people to come up with different answers because people make different mistakes. So it seems like there's 3 possibilities. Jesse could be right, Tracy could be right, or they could both be wrong. You know, it is quite possible that neither of them found the right antiderivative. Now the question is, how do we know who is right? Now here's the beautiful thing, is when you're looking for antiderivatives, you have a built-in check. So the question is, if I'm asked to find the antiderivative of, say, f of x, how do I know if I succeeded? Because you might say, well, I say, okay, maybe it's f of x. So this is our guess. Well, how do we check if our guess is right? Yeah, you take a derivative. So you know you found the right antiderivative, and this is our check. So you know you found the right antiderivative if the derivative of capital F of x is equal to little f of x. So there's always a way to check your answer when you're doing antiderivatives. So if you're not sure if you took the right antiderivative or not, just do a quick derivative, because derivatives tend to be pretty quick, and see if you got the same thing that you started with. And if you did, then odds are pretty good you did the right thing. And if you didn't, odds are pretty good you're messing up somewhere. So be careful and go back and think some more. Now in our case, this 2 times x plus 1 over 1 minus x quantity cubed, this is our little f of x. So now what we'll do is we'll check these answers. So let's start with Jesse. We're going to take the derivative of 1 plus x squared over 1 minus x quantity squared plus c. Now when we take the derivative of the plus c, the derivative of the plus c goes away. And that's why we say the answers are only true up to plus c. How do you take the derivative of 1 plus x squared over 1 minus x quantity squared? Quotient rule. So we're going to take the bottom term, that's 1 minus x quantity squared, times the derivative of the top, which is 2x, minus the top, which is 1 plus x squared, times the derivative of the bottom, which is 2 times 1 minus x to the 1 times negative 1. Because you need to remember it's a chain rule. The 2 comes down, 1 minus x to 1 less power times the derivative of 1 minus x, which is negative 1. Now all of this is divided by 1 minus x squared, 1 minus x, sorry, that's just 1 minus x quantity squared, and that's squared. There we go. I knew there were 2 squares there. Or if you like, this is really 1 minus x to the power of 4. Now, it doesn't look like that yet, but we know that there's the power of algebra, and it's a magical, beautiful thing. So let's use some algebra to help simplify. What do you notice about all 3 of these terms? They all have 1 minus x, so I'm going to go ahead and cancel 1 of the 1 minus x's. That'll get this to the 3rd power, and again, we've replaced downstairs. So that's promising, 1 minus x cubed. Let's see, what else do we have? All right. So we have 1 minus x times 2x. So that would be 2x minus 2x squared. So if I multiply this out, here we have a minus and another minus, which makes a plus. So if I multiply this will be times 2 times 1 plus x squared. So plus 2 plus 2x squared. So that'll be the numerator. All divided by 1 minus x cubed. The minus 2x squared and the plus 2x squared cancel. And we pull out a 2. So we get 2. And if you look, they say, oh, that's 2 times 1. And that's 2 times x. So 2 times x plus 1 over 1 minus x cubed. And so we say, aha, now we know. Who was right? It's Jesse. Jesse got it right. All right, are we done with the problem? We should check to see what Tracy did. Maybe we can figure out where Tracy made their mistake. Okay, so let's do the same process. All right, take the derivative. Now, we look at this and say, okay, hey, this looks a lot like another quotient rule. Again, the plus t goes away. So we're going to take the bottom times the root of the top, which is 2, minus the top, 2x, times the root of the bottom, which is 2 times 1 minus x times negative 1, because it's still the same denominator. All over the bottom squared, which would be 1 minus x to the 4th. Now, what would we do here? Cancel off a 1 minus x like before. All right. So, let's see, what do we have left upstairs? Well, we have 2 times 1 minus x. So that's 2 minus 2x. Ah, okay, 2 minus 2x. That's probably their mistake. Minus minus makes a plus. 2 times 2x is plus 4x over 1 minus x cubed. And that gives us a final answer of 2 plus 2x over 1 minus x cubed, which is 2 times 1 plus x over 1 minus x cubed. Haha. No wonder they made a mistake. See, they were trying to do 1 plus x and not x plus 1. No. It's okay. It's the same thing. So, what does that say about Tracy's answer? Tracy is also right. Now, this one you're like, what? So, like, all the functions are right antiderivatives? No, probably not. Okay, so how can they both be right? Because the functions look different. Magic? No. No. But it starts with the math. Okay, so are these in fact different functions? Well, we should have a basic belief that antiderivatives are true up to some constant. But here's the deception. See, in both cases, we wrote plus c. Now that's not wrong. We should write plus a constant. But it doesn't have to be the same constant. So what could be the case is that these two are actually the same function, except they differ by a number. Now how can we figure out if that's the case? Well, one way to tell if two things only differ by a number is just subtract them from each other. So if you took 1 plus x squared divided by 1 minus x quantity squared, and then you subtracted 2x over 1 minus x quantity squared, what you'd end up with is upstairs is 1 minus 2x plus x squared, and downstairs you end up with 1 minus x quantity squared, because 1 plus the x squared, then the minus 2x. But how does that upstairs change? It's 1 minus x squared. And so what's happening is that these two functions differ by a constant. So it turns out if I added 1 to this function here, so if I put a 1 plus, that would result in this function there. So it's okay if answers look a little bit different, because it's possible by perturbing constants, or maybe if you're doing trig, applying trig identities, it's possible to have different looking answers be correct, because you are allowed to be different up to a constant. So keep that in mind. All right, but also keep in mind we have a tool to check, and that's a really useful thing. So now on to a different topic. So antiderivatives, we're going to put that aside, because now we're ready to talk about our two forms of calculus. And we've already talked about differential calculus, and the basic question you ask in differential calculus, how are things changing? And the way we answered that, we just said, all right, I understand how lines change. Lines, they have their slopes, and slopes are a measurement of change. So I'm going to approximate things by a line by zooming in at that point until it zooms into something flat. That flat thing helps me understand what's going on, and I can answer the question of how something is changing. We're going to transition to a different topic. So instead of asking how are things changing, the new question is how much is there? In other words, what's the total? Now, I'm going to be very careful here. A lot of people think that the following part of calculus, which is integral calculus, is all about finding area. And we're going to use area to help build our geometric intuition. But it really boils down to a lot more than area. It's just saying what's the total. But picture-wise, when we're looking at pictures, area is really, really good for us. So for right now, we're going to talk about how much is there. So we're going to think about specifically area, but I'm putting that in quotes. Because remember, it's how much is the total, and it just depends on context as to what that total could be. As we go further along in calculus, including the next semester and the semester after that, we'll find that we can use integration to answer questions such as how much surface area is there to a three-dimensional shape? How much mass is there? If you go into finance, how much money is this investment going to make you? All sorts of questions can be answered using integration. So whenever you want to know the question, how much is there, that's an integration technique. Now we go back to differential calculus, and we said our basic idea was to say, let's approximate by things which are flat. We're not going to change that. So we start to say to ourselves, what's an object which is flat, which we know how to find the area for? So what can you think of that's a flat-looking object that we can find the area for? Rectangles. We know how to find the area of rectangles. So we say, aha, here's our idea. Instead of trying to find this area, which is all sort of curvy and not flat, what we'll do is we'll break things up into little tiny strips. So if you look, what we're doing is we're going from A to B, and we're really breaking A to B up into little tiny checks here. Boom, 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 boom. And for each one, I have the actual piece, but that actual piece looks like a rectangle. So I can approximate each little part by a rectangle. Now, it's not an exact thing, it's an approximation. Just like when you zoom in on a curve, it's not exactly flat. There's still a little bit of a bend to it. But we can get better. So what do we do to zoom in here? What's our idea? In other words, a better approximation. What should we do? More rectangles. So if you want to get a better approximation to the area, you use thinner rectangles. And the more rectangles you use, the better your approximation gets. And at this point, if you're not nervous, then I've failed to do my job. You should be nervous. Like, that looks like a lot of work. And the answer is yes. And I'm going to convince you of that over the course of the next 2 lectures. And then we're going to say, but there's good news. So that'll take about a week. When you hear the good news, you're going to be like, oh, that is good news. Okay. So that's our philosophy. Now, how do we do it? Well, so again, this is a picture to keep in mind. We're going to break things up into rectangles and add them up. So when we add things up, we call it sums, because to sum something means to add it up. And we call it Riemann sums, not to be confused with Riemann sums. This is Riemann sums. So there's a lot of information here, but if you just think back about what we're trying to do, it's like, oh, okay, this is not so bad. So our goal is we're trying to approximate the total area under some curve. So what's the approach? Well, we're going to break up our interval from A to B into little segments and say, well, let's look at each segment. each segment is going to have a rectangle that sits on top of it, that approximates the curve. So if I have a rectangle, I need two things. I need to know the width, which is, let's actually just look back at our picture here, because we have picture technology. So I need to know the width. So the width, I have some point here, I'll call it a sub I minus 1, and the next word is a sub I. So the subscript is just sort of convenient notation for us, because we have a whole bunch of these, so I just need to know the ith one as I move along. So the width here at the bottom, that's the difference between the two numbers. And so we're going to call the width, for lack of a better term, delta I. The width of the ith interval. The height, now here is where we have to pick a choice. We say, well, I need the height of the rectangle. And to get the height, as I pick some point in this interval, and I plug it into the function, and that is the height of the function. Now, it varies depending upon which point you pick, but here's the beautiful idea. See, if my rectangle is very thin, my function won't vary very much. And so that says that your height, it doesn't really matter which one you pick. The perturbation that comes from a different choice will be very small. That's why you want the thinner rectangles. The thinner the rectangle is, the smaller your arrow will be. So this point right here, this is our height. That's our function of xi. So now you have a width and a height, and so you get the area of the rectangle is this, I'll shade it in. That area is f of xi delta I. Now, that's just one rectangle. So you do it for each one of the rectangles going across. So that's what's happening here. The first rectangle, fx1 delta 1. The second rectangle, f of x2 delta 2, and so forth and so on. So the dot, dot, dot is a shorthand notation for saying, and the pattern continues. And then you go all the way to your last rectangle. So this is if we use n rectangles. Okay. And I suppose I should have shown that from the beginning. So we have our various pieces. Now, here's the big question. How do you pick the xi? Because if I come up to this interval, let's say I'm in this interval, I'll start with this one, from 1 to 2. What's the right one to pick? And the answer is there's not a right one to pick. It's just a matter of how you want to do it. So there's a couple of natural candidates. So there's the left endpoint, and if you pick the left endpoint, this would be your height. You could also pick the right endpoint, and if you pick the right endpoint, that would be your a sub 2, that'll be your height. So you'll notice that there is a difference depending upon which one you pick. Like I say, there's an error. Now what else could you pick? Well, you could pick a midpoint. So if I were to pick a midpoint, that would say, for instance, if I came here between A4 and A5, the midpoint would go halfway in between A4 and A5. And then that would be your height. In some sense, it feels like the midpoint is better at balancing things out. You can also pick where is the largest value and where is the smallest value. Now, the thing about picking the largest value and the smallest value is it's a little bit hard to do for a function, because in order to pick the maximum value and pick the minimum value, you have to find the max and the min. So you might come to this interval between 2 and 3 and be like, well, maybe the min occurs right there. But then you actually have to spot it, and that can be hard. But there are some special cases when you have a function which is well behaved, and you can actually identify where is the max value and where is the min value. All right. So we get into more of a discussion about this next semester when we do Calculus 2, because we see that there are times when we basically have to just embrace our need to do things by computation. All right, so let's do a nice problem. Estimate the area under y equals 4x squared for 0 less than or equal to x less than or equal to 4 by Riemann sums with 4 equal-sized intervals using the left endpoint, the right endpoint, and the midpoint. So let's go through our process. Now we can visualize what this is doing. 4x squared, what's that shape? It's a parabola. It's a parabola that's been stretched a little bit. So here's my parabola, and I'm going from 0 to 4. So here's 4. Now, we want to split 4 equal-sized intervals. Now what that means is between 0 and 4, I want to split this up so I have 4 equal-sized parts. So we want these to be equally spaced. So where will these points be at? 1, 2, and 3. So my 4 intervals are from 0 to 1, 1 to 2, 2 to 3, and 3 to 4. Those will be my 4 different intervals. All right. So we want to estimate the area here using Riemann sums. And we're going to do it 3 times. Left endpoint says what? Well, the Riemann sum says I look at the left endpoint. So the left endpoints would be 0, 1, 2, and 3. So for each one of my 4 intervals, I ask, where's the value that's on the left-hand side? So this will be the following. Oh, there's one other thing we need to identify. What are the widths of these intervals? 1. So this is important. We won't always have our widths be 1. And so it's important to keep your widths about you as you're doing these types of problems. Okay, so from the left endpoint, we get the following. It's going to be the function at 0 times 1 plus the function at 1 times 1 plus the function at 2 times 1 plus the function at 3 times 1. And what's happening is the times 1, that's the widths of the interval. So I have to multiply the widths by each term. The f's are the heights. So what's happening, if we were to sketch this, the first rectangle is a very, very tiny rectangle. It has no height. Because what is f of 0? It'd be 0. And then the second, well, I plug in 1. What do I get when I plug 1 in? 4. And then the next one, what do I get when I plug in 2? 16. And the last one, what do I get when I plug in 3? 36. So we add these all up. 4 plus 16 plus 36 gives us a grand total of 56. So that's our left. Okay, that's not so bad. I've actually shaded it in. So you can see that the left is going to be an underestimate because the function has a behavior where it increases as we move from left to right. And because it's increasing, if we use the left end, that's the low side. So now we're going to go to the right end. If the left end was an underestimate, the right end will be an overestimate because when we're increasing, the right side will be the largest point. So how do we pick those? Well, the answer is for each interval, we look to the right side. So our right sides are going to be at 1, 2, 3, and 4. So, similar process. For the first interval, we pick now the point at 1. For the second interval, we pick it at 2, and so forth and so on. You'll notice again I'm multiplying by 1 because our widths are still 1. Okay, what's the height of the first, or rather, what is f of 1? 4. What's f of 2? Yep. Oh, you're quick. What's f of 3? Oh my God, you're faster than I can do that. Okay. How about f of 4? 64. All right. And if you add these together, well, this would be 20 here. That would be 100 there. And so we end up with 120. So we've now narrowed it down to say that the total area is somewhere between 56 and 120. That's kind of a broad range. We'd like to be a little bit more precise, and we'll get to the right answer. I think we'll be able to do it certainly by the end of next time. But let's do the middle one. The middle one is probably more correct. And it might make you think a little bit more. Now, the widths are always going to stay 1. So what's halfway between 0 and 1? So that's the midpoint, 1/2. So it'd be f at the halfway point, 1/2 times 1. What's halfway between 1 and 2? 3/2. Or 1.5. What's halfway between 2 and 3? 5/2. And between 3 and 4? 7/2. All right. So if you plug in 1/2 into 4x squared, what do you get? You'll get 1. It'll be 4 times a fourth. Plug in 3/2 into 4x squared, what will you get? You'll get 4 times 9/4, which is 9. Plug in 5/2, what will you end up with? 25, because it'll be 25/4 times 4. Plug in 7/2, what will you be? 49. And 49 plus 1 makes 50, plus 25 makes 75, plus 9 makes 84. Not surprising that the midpoint is in between the left and the right. Because, you kind of would expect it to be in the middle. It sounds like a very middle thing to do. What's the right answer? Well, stay tuned. We'll tell you next time. Estimate the area under the curve y equals the square root of 25 minus x squared for 0 less than or equal to x less than or equal to 5. We're going to use Riemann sums with 5 equal intervals to give both an upper and lower estimate for the area. Now, do we know what this curve looks like? Y equals the square root of 25 minus x squared? It's a circle, yeah. Circle of what? What's the radius? 5. So what's happening here is we're trying to estimate the area for this circle. Now you're probably thinking, I can give you a really good estimate right now, Steve. Really, really good. Do we know what the answer is? 1/4 of the circle. How much area was there in the circle? Pi r squared. So the actual answer, before we start, we can even tell what it is in this case, is 1/4 of 25 pi. Now, we got lucky because they gave us a shape we know the answer to. They usually won't be so nice to us. So we're doing 5 equal intervals, so that means we want to split up the interval from 0 to 5 into 5 equal parts. Well, we're starting at 0. Where will our locations be? 1, 2, 3, 4. Yeah, they tend to be nice to us and give us numbers we can work with. Okay, so what do? Well, suppose we want to do an upper estimate. Now what that means is for each one of my intervals, so I'm going to sort of go up to the line here. We go up and we say, all right, if I want an upper estimate, I always pick the largest value in that part. So between 0 and 1, where do I hit my maximum value? I hit it at 0. So for the first interval, I'm going to see what happens at 0 times by the width of 1. For the second interval, between 1 and 2, where do I hit my highest point? At 1. Times the width is 1. How about for the next interval? The highest point will be at 2. Now, you're probably thinking, this doesn't seem that different from what we were doing just a moment ago. And the reason it feels that way is because our function is very well behaved. So this function, square root of 25 minus x squared, it's decreasing. So as we go from left to right, it's going down. Which means if I want an upper bound, I want to pick the left endpoints. Now, your function does not always have to have the same behavior. So in other words, it might not always be monotonic. And remember, that's just a fancy way of saying you have one behavior. And so you have to be flexible and say, okay, where does it happen? Now we can read off our answers pretty quickly. What is f of 0? Plug 0 into our function. 5. F of 1? Square root of 24. F of 2? Square root of 21. How about f of 3? 4. F of 4? 3. So we get an upper bound of our answer is 5 plus 4 plus 3. That makes 12. Now 24 you could be fancy and say, that's really 4 times 6. So you could write it as 2 root 6 if you were being fancy, but you don't have to. You can leave it as square root of 21. Square root of 24, and then you have the square root of 21. So that's an upper bound. Now if you're doing the lower bound, what do? Well, similar process. What's the only difference? Yeah, for each interval we pick the lowest points. Previously they were the left was the high point. Now it's the right is the low point. So it's f of 1 times 1, f of 2 times 1, f of 3 times 1, f of 4 times 1, and f of 5 times 1. Now most of these values are ones that we've already talked about. So the only one that we didn't talk about was what happens when you plug in 5. So what does happen when you plug in 5? 0. So our lower bound is 7 plus 2 times root 6 plus the square root of 21. So we can come to the conclusion that 7 plus 2 root 6 plus 21 is less than or equal to the actual value, 25 fourths pi, is less than or equal to 12 plus 2 times root 6 plus square root of 21. Now, you probably are saying, these are big gaps, because there's a gap of 5 between the upper bound and lower bound, and the gaps will be fairly large. The way you get your gaps small is you have to get really small intervals. So we have to figure out, how do we get really small intervals? How do we even do the notation for that, and how do we make that work? So let's start with the notation, because if it's one thing that we all love, it's good notation. So here we go. So what we do is practice a little bit of Greek. So we want to have a way to sort of compress a big sum into a compact form. Another way to think about it is we want to have a nice way to say, what is this dot, dot, dot? So dot, dot, dot is really a shorthand mathematical way of saying, and the pattern continues. So we just want to be explicit. Here's what the pattern is. And here's where you start. Here's where you stop. And this is what you do. So here's how you do a sum. The big thing here is this Greek letter sigma. Now, why do we use the Greek letter sigma? Well, because the sigma is associated with S. And S is for sum. So that's why we choose the sigma. S is for sigma. That's what it means to me. Right? Yes? No? Okay. All right. Anyways, so S for sigma. S for sum. So that indicates we're doing a sum. Now, if I need to do a sum, I need to know where to start and where to stop. So this lower thing where it says start at P, end at Q. So P and Q are where you start and stop. Then I need to know what I'm adding. Now, what I'm adding depends on where I'm at in the process. Because I say I'm starting at some point, maybe at 0, and I'm ending at 4. Or I'm ending at 5 or something. So I need to say, well, where am I at any given time? So you have this thing called K. Now, K can vary depending upon what you like to use. Some people use I, some people use J, some people use K or L. But it's an index. Now, I call it a dummy variable in that it doesn't really show up in your final answer if you were to write it out. It's just used for convenience. So you can change it to make it something more convenient. So that K keeps track of where you're at in the process. It starts at P and it goes to Q. And now you say, okay, what is it you're adding? Well, that's the A sub K. Now, the reason there's a sub K there is it says, I need to know what is my kth term? So oftentimes the a sub k is some function of k. So maybe I'm adding up k or k squared or something. So this notation, it's fairly shorthand. It's just a short way to write out this expression. See, we started at p, so that's why the first term is an a sub p. And then you go to the next term, a sub p plus 1. And the next term, a sub p plus 2. And so forth and so on. Till you get to the last term of a sub q. So this is just a notational way to write a long expression into a short form. Once we have that, it helps us to do manipulations so that we can start doing things in a short, fast way. So let's write out some sums just so we make sure we understand the notation. So suppose we're adding up the sum from k equals 2 to 6 of k minus 4. So we're going to start at 2. If we put in 2, what do we get? We'll get negative 2. So this is our k equals 2 term. Now you put in 3. What's the next term going to be? Negative 1. Now, so next term would be 4, 0. Next term will be 5, 1. Next term will be 6, which is 2. And stop. Because you start at k equals 2, and you stop at k equals 6. So we're going from k equals 2 to k equals 6. Now, we're just asked to write out the following sum. We could simplify this. It turns out this simplifies very nicely. But we don't have to simplify. So there's k equals 2, k equals 3, k equals 4, k equals 5. I'm just emphasizing what's happening here. I won't do this with all of them. So you can see the process. Okay, how about the next term? Sum k equals 3 up to 7 of k squared. What does the first term look like? Well, so the first term is 3. So the first term will look like 3 squared. What's the next term look like? 4 squared. And 7 years ago. Oh, wait, no, that's something else. 5 squared. Oops, I should probably write a square like a 2. Next one? 6 squared. And then? 7 squared. And? Stop. Because we're only going from 3 to 7. So it says start at 3, write the square numbers. 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, and then stop at 7. All right, now let's look at this next one. 1 to 5 of j plus 2 quantity squared. Well, what happens when you plug in 1? You get 3 squared. When you plug in 2? 4 squared. When you plug in 3? 5 squared. When you plug in 4? When you plug in 5? And then stop. Now let's pause for a second and say, wait a second. Wait a second. These are the same. Whoa. Does that mean it's possible to write the same sum in different ways? And the answer is yes. Yes, it is possible. Now how? Well, what essentially we're doing is we're changing our dummy variable. So let's think about what's true. What's the relationship between these two is they're really, instead of here you have k, down here you have j plus 2. So you can get from one to the other by doing a change of names. So if you say, look, everywhere where I see a k, I put j plus 2. Well, if I put j plus 2 squared, I'd have j plus 2 squared. Suppose I had, okay, k equals j plus 2. J plus 2 equals 3. What does that translate into? J equals 1. Now you're probably thinking, aha, but Steve, you have a problem. What is the 7? Well, see, secretly, we often suppress the notation. But when we write 7 upstairs, we really mean from k equals 3 to k equals 7. So if I think of j plus 2 equals 7, where would I stop? At j equals 5. So you can do this sort of change of indexing. And this way to manipulate sums is a really cool thing to do. Something that, again, Oh, there's so much to look forward to when you do Calculus 2 next semester. It's going to be a lot of fun. Okay, 2 more to go. All right, we'll speed up. So we're summing from k equals 0 to 5 of 2 to the k divided by k plus 5. What's the first term look like? 1 over 5, because 2 to the 0 is 1, and 0 plus 5. What's the next term look like? 2 over 6. Next term? 4 over 7. And you could have written the 4 as 2 squared. And I could have written this as 2 squared over 2 plus 5. But I don't have to. Okay, next term? 8 over 8. Which I could have written as 1, but that's all right. Next term? 16 over 9. And I think we need one more. 32 over 10. So again, what we're doing is we're taking this expression and simplifying it. And the last one, 1/6 times 1 plus k over 6 squared. Now, if you do this, what do you get? Well, you get 1/6 times 1 minus 2 over 6 squared plus 1/6, 1 minus 1 over 6 squared plus 1/6 times 1 plus 0 over 6 squared. You'll see, at least, I don't know if it's coming across in my tone of voice, it's like, wow, this takes a lot of time. Do we really want to be investing time in doing this? Well, oftentimes we don't write this out term by term. The real thing is we want to just get a practice of saying, I know what these things look like, and I know what to do with these. Now, what are things we can do? Well, we have a few basic properties of sums. So 2 of them, well, let's just start here. The first one says that sums behave like sums. In other words, you can rearrange them, and you can also pull things out. So sums respect addition and constants. If we use the language we've been using throughout the semester, we could say that sums are linear. So we can break them up over addition, we can pull constants out. And that's really, all that's happening here is you're just rearranging your sums. And it's very, there's a typo here. This was supposed to be the good lecture notes. I forgot to put my upper index. There's nothing profound going on here. It does what you think it should do. The second thing that shows up here is actually what we talked about in the example, which says that, hey, you can do a reindexing. So that's what we were talking about here. You're allowed to reindex your sum. Because this is a dummy variable, by changing the names, you can still have the same sum. Because these are 2 ways of writing the same expression. You'll see here, I start at a sub p, and I keep going until I get to a sub q. If you plug in here, you have p plus r minus r, which means you start at a sub p, and you go until you get to a sub q, because it's q plus r minus r. So these are just a change of index, like we talked about here. Now, to be really useful, it's good to know a couple of basic sums. And we will not test you on knowing these things. So don't panic and say, I have to memorize these things. That's a Calc 2 kind of thing. We're just Calc 1. We just get to admire them and appreciate their art. So some of these are pretty easy to convince yourself they're true. For instance, if I add 1 plus 1 plus 1 plus 1, and I keep doing that n times, so let's see if we can do this. So it's 1 plus 1 plus 1, and I do this n times. What's my final sum going to be? N. Okay, that's pretty convincing. Now, this one says I'm going to add 1 plus 2 plus 3 all the way up to plus n. And that's not so obvious what that should be. But here's a way to figure it out. Okay, let's suppose we didn't know what the answer was. Let's call it S, because it's the sum we want to figure out. Well, it turns out that S is the same as n plus n minus 1 plus n minus 2 down to plus 1. In other words, instead of adding from 1 up to n, let's add n up to 1. I'm still adding all the same numbers together. I'm just reversed the order I add the numbers up. That's still s, yes? Okay, all right. Let's tally. 1 plus n, what is that? It's n plus 1. 2 plus n minus 1, what's that? N plus 1 again. 3 plus n minus 2? N plus 1. And we get to the very end, what is n plus 1? N plus 1. Now that's going to be equal to s plus s, which is twice s. How many terms do we have? Well, we have one term for each thing we started with up above, which means there are n terms. So if I add n plus 1 up n times, what do I end up with? N times n plus 1. That's equal to twice what we're trying to find, and therefore what we're trying to find is n times n plus 1 over 2. There's that one. Now, the sum, this one, this is 1 squared plus 2 squared plus 3 squared and so forth and so on. And we'll just go on faith on that one. It's a little bit trickier to show. It can be shown, but okay. The last one, this one is good. You should know this one. So this says what? You're going to add r plus, the next term will be r squared, and then the next one will be r cubed. And you keep going all the way till you get to r to the n. Now I'm trying to figure out what that sum is. I'm going to call it s. Now this is called the geometric sum. Geometric, in case you're wondering what does geometric mean, geometric means multiplying. So you're multiplying at each stage. So what we're going to do is we're going to multiply everything by r. Now if I multiply r times r, what do I get? R squared, yes? Then r squared times r is r cubed. And that's going to continue all the way down until I get to the very end, r to the n plus 1, right? Now that's going to equal to r times s. Now here's what we'll do. Let's take this second equation and subtract off the first one. If we do that, well, you'll notice a lot cancels. R squareds cancel, r cubes cancel. Everything cancels. Well, not everything. Wait, what didn't cancel? R to the n plus 1 didn't cancel. And then there was a minus r that didn't cancel. But that's equal to r times s minus s. So that's equal to r minus 1 times s. And therefore, s, the sum we want, is r to the n plus 1 minus r over r minus 1. Now our stage has been set. We have our sum notation. Where do we go next? Well, where we go next is we go back to the Riemann sums. And now we can actually start finding some answers using Riemann sums, using things that we know. Not just estimates. We're going to go all the way. But we'll do that next time. That's it for today.